Index notation. Seems a bit tiresome writing 5 times 5 times 5 times 5 times 5 times 5. There's 6 of them. So someone invented a shorthand way of writing it, and we write it like that, 5 to the power 6. This means that there are 6 of these 5s multiplied together. And then we notice that there are certain things, certain rules that these obey, such as if we've got 5 squared times 5 cubed, that's a special way of saying 5 to the power 2 times 5 to the power 3, we could write it out in full like this. And we notice that there are 5 of them in total, so 5 squared times 5 cubed must equal 5 to the power 5, 5 of them multiplied together in one go. So what's clear is that the number here, 2, and the number here, 3, add together to make the number in total 5. So that gives us our first law of indices, that when you multiply two things with the same base you add the indices. What about division? Well, 5 to the power 7 divided by 5 cubed, don't know why I'm using 5 but I will do, is 5 times 5 times 5 times 5 times 5 times 5, how many is that? 6 times 5 divided by 5 times 5 times 5. And then, as with any fractions, we can do some cancelling. Cancel that with that, cancel that with that, and cancel that with that. And we're left with 5 to the power 4. And what's happened here is that the 3 at the bottom have cancelled with 3 at the top. In other words, these 3 have cancelled with 3 of the 7 to leave 4. And that's our second rule of indices. Law of indices, when you divide the same base you do a subtraction. But what if there's more on the bottom than on the top? What if we've got 2, something like 2 to the power 2 divided by 2 to the power 5? Well, that's 2 times 2 divided by 2 times 2 times 2 times 2 times 2. We get a bit of cancelling here, that cancels with that, that cancels with that, and this time we've got 3 left on the bottom rather than on the top. So that must equal 1 over 2 cubed, which we knew anyway. But our law of indices tells us that when you have things with the same base, such as these are, both base 2 is what we'd say, you subtract. That's what we saw before, so it should be 2 to the power 2 minus 5, that's minus 3, 2 to the power minus 3. So it should be 2 to the power minus 3, whatever that might mean. Well, it must mean 1 over 2 cubed. So negative indices mean reciprocals, 1 over. So far we've made sense of positive indices. 2 to the power 8 means 8 2's multiplied together. And using our laws of indices we found that 2 to the power minus 3 would equal 1 divided by 2 cubed, like that. So we can make sense of any positive number now. 2 to the power 0 must equal, well, 2 to the power 0, using our law of indices, remember when you divide you subtract, so it must equal 2 to the power 5 divided by 2 to the power 5. Nothing special about 5 other than that must be 2 to the power 5 minus 5, which is 2 to the power 0. Now what is 2 to the power 5 divided by 2 to the power 5? Well, anything divided by itself must be 1. So anything to the power 0 must be 1, so we think. And 2 to the power 1 must equal 2 to the power 3 divided by 2 squared. Nothing special about 2 and 3 other than when you do this subtraction you get 2 to the power 1. Well, 2 cubed is 2 times 2 times 2, and 2 squared is 2 times 2. That cancels with that, that cancels with that, and we're just left with 2. So 2 to the power 1 must be 2. In other words, a power 1 just means one of them, like that. So far then, we've made sense of all positive numbers, all negative numbers, also 1 and 0. So 2 to the power 0 equals 1, 2 to the power 1 equals 2, 2 to the power 4, well that equals 2 to the power 4, which actually is 16. I'm not that bothered about that though. And 2 to the power minus 4 equals 1 over 2 to the power 4. But what about other numbers? What other numbers are there here? You say, well, there are fractions. What does 2 to the power a half mean? Well, if 2 to the power 4 means 4 2's multiplied together, then 2 to the power a half means we need 2 of them just to make 2 to the power 1. 2 of these lot multiplied together just to make 2 to the power 1. And we can see using our laws of indices that that must work, because when you multiply you add the indices, and half add half equals 1. So this number, 2 to the power half, whatever it is, it's the number which when you multiply by itself, in other words you square it, you get 2. What number is that? Well, the number which when you square it you get 2 is called the square root of 2. So 2 to the power half must be the same as the square root of 2. What's 2 to the power a third then? It's that we need 3 of them just to make 2 to the power 1 using our laws of indices. So 2 to the power a third must be the cube root of 2 because we need 3 of them multiplied together to make 2. And this gives us a general rule for anything, that 2 to the power 1 over 9 would be the 9th root of 2, whatever that is, and 2 to the power 1 over 86 would equal the 86th root of 2. And just like before, if we've got 2 to the power minus a half, well, we multiply it by 2 to the power minus a half, we get 2 to the power minus 1 using our laws of indices. So 2 to the power minus 1 is 1 over 2, you'll remember. So 2 to the power minus a half it must be 1 over the square root of 2. It's the square root of a half, or 1 over the square root of 2. 2 to the power minus a half equals 1 over the square root of 2, which is also the square root of a half. What about 2 to the power 3 over 2? Well, if you multiply 2 of these together, you don't get 1, you get 3 over 2 add 3 over 2, which is 3. So this number itself must be the number which when you square it you get 2 cubed. In other words, it's the square root of 2 cubed. And we're beginning to see a pattern here, that this is a root, this is a power. So this is 2 square rooted cubed. 2 square rooted cubed. And it doesn't matter if you do 2 cubed square rooted, it gives you the same thing, but it's easier to make the numbers smaller first. So what's this? 8 to the power 4 over 3. Well, that must equal 8 cube rooted and then raised to the 4th power. The cube root of 8 happens to be 2. I wouldn't be so stupid as to make it difficult. To the power 4, which is then 2 times 2 times 2 times 2, which is 16. So this number is 16. Here's some questions to think about. If anything to the power 0 is 1, and 0 to the power anything is 0, what is 0 to the power 0? Is it 1? Is it 0? Maybe try on a calculator, see what you get. And also, we've looked at all fraction powers. At the bottom of the fraction represents a root, at the top of the fraction represents a power. But what if it's not written as a fraction? What if we want to do 2 to the power square root of 2? How do we even work out what this is? Your calculator will tell you, but what's it actually doing? Here's a question. Can an irrational number to an irrational power ever be rational? This leads to one of the best proofs that you'll ever see. Here it goes. Well, let's look at the square root of 2, an irrational number, to the power square root of 2, an irrational power. Well, is this rational? If it is, then the answer is yes. So if this is rational, we've found something which an irrational number to an irrational power which is rational. So the answer is yes. But what if it isn't? What if it's irrational? Well, it doesn't mean our answer is no, it just means that this particular one, the answer is no. It doesn't mean we're never going to find one. So let's look a bit deeper. So now, either the square root of 2 to the power square root of 2 is rational, in which case we found one, or it's irrational, in which case we need to look further. Well, if it is irrational, how can we look further? Well, what we can do is this. We can take our irrational number and raise it to an irrational power. Big deal, you say. Well, let's have a look, see what this is. This is the square root of 2 using laws of indices to the power 2. Laws of indices tell us that when we've got something raised to a power, we multiply these indices, and root 2 times root 2 is simply 2. And root 2 squared, this number that we've just produced, is 2, which is a rational number. So what have we shown here? We have shown that either the square root of 2 to the power square root of 2 is rational, or this irrational number to an irrational power is rational. In other words, if you think about it, we have proven But yes, an irrational number to an irrational power can be rational. We don't know which one is irrational to a power irrational, but we do know that one of them will be. Even more bizarrely, if you were to study FP2, you'd come across Dumoire's theorem. Now, if theta is pi by 2, we get this. And we know that the cosine of pi by 2 is 0, so we get that's e to the I pi by 2 must equal, well, sine of pi by 2 is 1, so that gives us that result. And what if we then raise I, the imaginary unit, to the power I? Well, that must be the same as I to the power I, which is e to the I pi by 2 times I times I is minus 1, so that's e to the minus pi by 2. Now what this tells us is that we found an imaginary number to an imaginary power, and the answer is a real number. Maths gets weirder and weirder.